So in this work, I developed a formalism to quantitatively find whether the H2 regions have had the energy to push the magnetic field and orient them tangential to the surface of the bubble. And we actually see that there are a number of bubbles here, and quite a few of them have had the energy to push the magnetic fields, in this case to orient them completely tangential, in other cases somewhat tangential to the surface of the bubbles. In the region that we have very dense star-forming cores within this cloud, where the gravity is dominant, we see that the H2 regions actually did not have the energy and the time to push the magnetic field and orient them tangential to the surface of the bubble. So just by looking at the morphology of magnetic fields here, we can find regions where gravity is dominant, find regions where H2 regions and turbulence and outflow are dominant, and find regions where magnetic fields are dominant. So, so far I've talked about starlight polarization, dust polarization. We also need line of sight magnetic fields. So for line of sight magnetic fields, we can use Faraday rotation, which is the rotation of the linearly polarized electromagnetic wave in a magneto-ionic medium. The amount of rotation is given by this formula that you may be familiar with, and the amount or the quantity in parentheses is known as rotation measure. There are three main techniques that can use Faraday rotation in radio observation to find line of sight magnetic fields associated with different regions. In the classical technique, we can use extragalactic point sources to find the magnetic field associated with the large-scale galactic magnetic field or a highly ionized region. So the first technique finds just magnetic field associated with either very large or very ionized regions. The second technique, which is Faraday tomography, decomposes polarized light into components of rotation measure along the line of sight. So we can investigate these components of rotation measure and find correlations with physical distances. And then the third technique, which is a technique that they developed in 2018, allows us to find the line of sight magnetic fields associated with molecular clouds. In this technique, again, we are using extragalactic sources. In the Faraday tomography technique, we are using extended emission, but in the first and the third technique, we are using just point sources. So could be either pulsars or extragalactic sources. I won't talk about the third technique, but I'm happy to answer any questions. Briefly, it's based on an on-off measurement and also using column density maps and chemical evolution code. So the result of technique, we find it consistent with Zeeman observations. When we look at molecular regions, our results are consistent in strength and in their direction with molecular Zeeman observations. When we look at the outskirts, our results are consistent in direction with atomic Zeeman observations. And also in terms of strength, when we compare with Zeeman, we find fascinating correlation as well. And so in this case, in a number of molecular clouds, Here I'm showing Orion A. We find a reversal across these clouds. So here the circles show line of sight magnetic fields. Red show magnetic field pointing away from you. Blue shows magnetic field pointing toward you. And we see that at one side to the other, magnetic fields point reverse from one side to the other. Okay, so we have line of sight, we have a tomography of plane of sky, and we have plane of sky. For line of sight, I like to mention that we've developed software, MCB LOS, with a number of excellent students who have contributed to the development and testing of the software. The software is available on GitHub. Please download it, play with it. We very much welcome any feedback from the community. And if you like to extend it to a certain region, a non-molecular region that you're interested in, we are happy to work with you to extend the capabilities of this software to more regions. For example, right now we're working to extend the software to non-thermal filaments. So when you download the software with the initialize command, all the data, including the required packages, the config files, the cloud maps, and rotation measure catalogs are automatically downloaded on your computer by this command. And then by this command, after changing the cloud of your choice in the config file, it runs a series of steps from making the directory for the cloud, finding mapping rotation measure, providing a series of diagnostic tools to find the line of sight magnetic fields associated with the molecular cloud of interest. The user also has the option to run this on multiple clouds at once. We don't have parallel processing at this time, but with one command, you can run this on multiple clouds. And we have a user manual and also the paper that describes this software. Okay, so we have the software, we have plane of sky observations. Let's see how we can get to 3D magnetic field observations. So for 3D magnetic field observation, one step is to, so what I did here is to get our plane of sky. So here, Planck plane of sky magnetic field observations and our MCB LOS line of sight magnetic field observations. And then here, using a series of Monte Carlo analysis, investigating a range of systematic biases and chi-squared probability values. In the case of Orion A that we were showing before, we concluded that an arc-shaped magnetic field morphology, the magnetic fields bend around the filamentary structure, is the most probable candidate to explain this magnetic field reversal that we are showing. So the second step is constructing models and comparing observations with models. And one thing I should mention here is that we are confident that with the technique that we've developed, we are probing both the molecular regions with the dust and with the line of sight magnetic field observations. So here, so far we know it's arc shape. We don't know whether this arc is concave from our point of view or convex from our point of view. In this case, we next use galactic magnetic field models, plane of sky and line of sight magnetic field observations. And we are only interested to look at the coherent component of galactic magnetic field models. And in the coherent component of galactic magnetic field models, these models actually match with each other. There are different models, but these models in the coherent component match with each other significantly better compared to if we have the turbulent component. And we are interested in the coherent component because we want to see how the magnetic field would look like before the evolution in this region and before the formation of the cloud and the evolution of the cloud. So using this technique, we actually developed or reconstructed the complete 3D magnetic field vectors for Orion A and Perseus molecular cloud. So we've seen Orion A now, let's switch to Perseus. So here I'm showing the Perseus molecular cloud. Again, the dots show the line of sight magnetic fields, and the red vectors show our coherent or our modeled galactic magnetic field, which is somewhat parallel to the plane of the sky. And the 3D magnetic field that we reconstructed is concave from our point of view and points in the decreasing longitude direction. So we know which direction it's pointing, and we know that it's concave. And this arc-shaped magnetic field morphology actually has been predicted in some cloud formation models. For example, the cloud formation model of Inotsuka et al. 2015, where a multi-compression is needed to form dense filamentary molecular clouds. So this arc-shaped magnetic field morphology continues to the rest of the galaxy and just has a sharp arc shape behind this cloud, or behind the Perseus and Orion A clouds. So now let's compare with the cloud formation model of Inotsuka et al. 2015. Using velocity information and magnetic field, we made predictions and found it consistent with the cloud formation model of Inotsuka et al. 2015. So we look to see if there are any bubbles in this region. And we know that we have the Pertau bubble identified in this region, where Perseus is located behind this bubble. And we already know that bubbles can push the magnetic field and orient them tangential to the surface of the bubble. We discussed this previously in terms of H2 region, but we know that this also has been observed for supernova regions using radio observations, for example, in the supernova remnants observed by Roland Cothas and Joanne Brown. Okay, so let's say that we know the orientation of the magnetic field before this bubble was formed, as modeled by our galactic magnetic field model using its coherent component. So the bubble would, and we have modeled the galactic magnetic field, so we have that. This Pertau bubble would push the magnetic field and bend it around the bubble of Pertau bubble, or around the shell of Pertau bubble. Would this explain the reversal that we are seeing? No, it won't, because the reversal that we are seeing is seen through measurements that previously had high uncertainties, and it's directly associated with the Perseus cloud. So I propose that there must be another structure, perhaps behind this cloud or Perseus cloud, that has further interacted with the field lines and pushed both the H1 gas and the field lines around this Perseus cloud, and resulted in a sharp arc-shaped magnetic field morphology directly associated with the Perseus cloud. So the cool thing is that, and my voice is disappearing, sorry. The cool thing is that after we put this paper on arXiv, the presence of this second structure was confirmed by Kunkel et al. 2022 using kinematic observations. So not only we reconstructed the complete 3D magnetic field, we were able to explain a step-by-step scenario for the formation of these clouds using 3D magnetic fields. And also, we were able to identify structures that were invisible to total emission observations. So this shows the power of 3D magnetic field observations that act as invisible threads and enable detection of structures that are otherwise invisible to total emission traditional observations. And we are now extending these techniques to more regions, particularly external galaxies and also regions within our own galaxy that are diffuse and extended. We are working on also on an SKA book chapter, so please stay tuned for the SKA book chapter that we discuss various 3D magnetic field vectors with the square kilometer array and its pathfinders. So extending to external galaxies using Faraday tomography, for example, in the study that we did led by Larry Rudnick, or dust polarization in studies led by Enrique Lopez Rodriguez or Borlaug et al. 2023, and also using rotation measures, so background sources led by Laila Jung. In 2014, we can extend these to external galaxies. And to add to the precision of these studies, we also need in addition to Faraday tomography, we also need to extend our observation with optical polarimetry. In optical polarimetry, I'm leading the efforts to make polarimetry observations with the Dragonfly telescope. Dragonfly telescope is an optical telescope composed of 48 Canon, commercially available Canon cameras stacked together and making some simultaneously observations. And after the observations are done, these images are stacked together. So the PIs of the Dragonfly itself were Bob Abraham and Peter Van Dokkum, and this telescope started in 2014 and was able to have a significant legacy in dark matter studies and identify or coin a new class of objects that were actually seen in some observations before, known as ultra-diffuse galaxies. And with these very faint observations, we would like to make full Stokes, so linear and circular polarization observations. So the Dragon...
May I use? Please wrap up in 5 minutes.
Sure. Yeah,
Thanks.
I'm done. So the Dragonfly, we have finished the lab experiments. The other PIs of the telescope or this project for polarimetry are Deb Lockhorst and Leo Holberg. And please visit our website. So I would like to wrap up by saying that from optical to far infrared, I'm sure that we will have talks about the square kilometer array and PRIMA. So with all these, we will be able to have 3D magnetic field observations associated with our Milky Way and beyond our Milky Way galaxy. And I'll just leave my summary slide, and I'm happy to take any questions.
Okay, thank you very much for that talk. So any questions from the audience? Yes, Kim?
Yeah, so thank you very much, Manoj. It's Tim. So it's a very beautiful talk. Yeah, so you are discussing the implication of 3D magnetic fields to understand molecular cloud formation. But I would like to put in the other way. So if we now get the 3D magnetic fields from your technique, we would be able to constrain the dust properties and also the dust physics across multiple scales, especially in extragalaxy environments.
Absolutely, yes. That's a fascinating comment and question. Yes, so with these 3D magnetic fields, especially since we have the full 3D magnetic field, we are able to further explore dust properties. And actually, one of our goals with Dragonfly polarimetry is, especially with full Stokes polarimetry, is explore dust properties better.
Especially if it has a circular polarization, I think it would provide the additional information about the dust properties.
Yes, yeah. So we had an initial chat a year ago about this. Yes. Please let's keep
Yeah, I
discussing
think
about
we would like to discuss further for our collaboration. Yeah.
Absolutely.
Thank you.
Thank you.
So Hamin,
Hi.
I'm Chop. So very nice talk. So as far as I understand that in order to get a magnetic field strength along a line of sight, we need to somehow estimate the volume density of electron, right? And you said that you use the chemical network. So can you elaborate a little bit more what kind of the evolution, chemistry evolution, and how we can estimate the volume density of electron in different environment, because we are in the Milky Way cloud and also the extragalaxy, so it seems different, right?
Yeah, excellent question. So any chemical evolution in our software can be used. We have output from a chemical evolution code that was developed by René Plume previously, but the user in the software can input any chemical evolution that they use. And I do understand that these chemical evolutions have uncertainties associated with them. So even though this technique is significantly faster than Zeeman, and we are getting consistent results in terms of strength and direction with Zeeman observations. For the strength, I still rely on Zeeman observations. So Zeeman remains as the most accurate technique to provide the strength. But our technique is providing a much faster technique to provide the line of sight. So for this technique, when we using the chemical evolution code that the software has, we compared for some regions with available publication for electron densities, and our results were consistent. However, there are uncertainties, so I would trust Zeeman in terms of the strength. we would like to keep working on improving the electron density estimates. So if you have measurements to improve that, we would like to welcome you to collaborate with us.
Hi, Manoj. Thank you very much for a very nice talk. And I have a technical question. Could you go back to the slide number 33 or number 34?
Sure.
Yeah. Yes. There are points. There are observations where very close by points where we have. I mean, the directions of the fields is very complex. It's going away from us and coming to us. For example, the 2 points at the end of the filaments, the bottom of the filament, and in the next slide we also have the same. I think so. Could you elaborate a little bit on that kind of observations? Yeah.
Yeah, that's a great observation. Yes. So we have VLA observations to actually address this, like exactly where we are seeing this curve. So kind of like a double curve in Planck, we see like magnetic field reversing and then reversing and then reversing. So in these observations, we did not have the resolution to address this, but we now have VLA observations. The data have been reduced by a PhD student, and she's working on publishing the rotation measure data. And after that, we will publish the line of sight magnetic field. But that's a great observation. So this magnetic field that we reconstructed is only giving us the kind of large scale magnetic field associated with the cloud. We are ignoring small scale fluctuations like this, but in the upcoming study, we're hoping to address that.
Okay, the last questions.
Hi, Manoshi. This is Jie. Thank you for the nice talk. So in this figure, I think the size of a circle is the strength of the magnetic field strength. So is there any reason the blue shifted magnetic field strength is larger than the red shifted one?
Yeah. So one thing I should mention here, that's also another great observation. One thing I should mention here is that I'm showing the line of sight magnetic fields here without their uncertainties. So generally the uncertainties need to be taken into account, but the point you mentioned is correct. In the denser regions, we see that magnetic fields are typically, line of sight magnetic fields are typically smaller. And that's because we are looking at line of sight averaging. So we start from the outskirts of the cloud and then get into the denser regions of the cloud and then again outskirts of the cloud. And because in the denser regions we have more fluctuations, probably more reversals, we have more rotation measure cancellation as well. And we end up getting a smaller line of sight magnetic field.
Okay, thank you.
Okay, thank you very much. So guys, thank our speaker again.
Thank you so much, everyone.
Yeah. Thank you, Manush. And then we can move on to the next talk. So, Yue, is you there? Are you there?
Yeah, I'm here. Can you hear me?
Okay, great. Our next talk will be given by Yue about studying 3D magnetic field with AI. You can start whenever you are ready.
Hello everyone. I'm Yue, and I'm very sorry I cannot make it in person this year. But I do want to thanks for the organizers invite me again to the nice workshop. So I will talk about how to predict the three-dimensional magnetic field but use a different method involved with artificial intelligence techniques like machine learning techniques. So I think in this conference, we have talked a lot about the importance of magnetic field in ISM. Like a magnetic field is important in identify the source of ultra high energy cosmic rays, and that requires the knowledge of large scale magnetic field. And the magnetic field is also important in regulating the star formation or the growth of galactic nuclei. And it's also important in modeling the foreground polarization, so we can detect the primordial gravitational waves signature. And as we already heard about in yesterday's talk and also Manush's talk, we have typically we have 4 approaches to trace magnetic field. The most common way is dot polarization, and typically it can only give the orientation of 2D magnetic field, a 2D magnetic field on the plane sky. And of course, if you are interested in the ionized phase ISM, you can also use synchrotron polarization, and that can also tell us the 2D magnetic field orientation on the plane sky. And the Zeeman splitting and farther rotation can directly detect the strength and sign of line of sight magnetic field strength. And as shown in Manush's talk, if we have multiple wavelengths observations, we can also infer the 3-dimensional magnetic field structure from the farther rotation and the Zeeman splitting. But here I would like to also mention there are some limitations in the traditional polarization or Zeeman and farther rotation method. The first one is it can only detect the integrated magnetic field. That means the polarization signals is integrated or collected along the long side. Therefore, what we get is only the projected magnetic field on the plane sky. But if we wanted to know the full picture of galactic magnetic field, and still we need to know the 3D spatial distribution of magnetic field with the magnetic field. And the second limitation is it can only directly detect the 2D magnetic field orientation or magnetic strength. And but that's true for several years ago, but I think in Ball's talk, he will talk about how to get the inclination angle and to infer the 3-dimensional magnetic field from a dust polarization. And here, in my talk, I will also talk about not just the inclination angle, but how to get the 3D magnetic strength. Then that can give us a full picture of magnetic field, including the position angle, the inclination angle, and the strength, total magnetic strength. So let's see how can we solve the first questions is how to get the 3D distribution of magnetic field in ISM. The idea though is very simple. We are not relying on the polarization observations, but we are using spectroscopy observation. That's because the spectroscopic observation can provide the velocity information along the outside. And if we use the velocity information combined with galactic rotational curve, we can determine the 3D position of a cloud, whether a Monarch cloud or H1 cloud in the Milky Way. Then if we can use spectroscopic observation to detect the 3D magnetic field, then we can get the 3D spatial distribution of 3D magnetic field in the Milky Way. And the spectroscopic observation, like the H1 observation, typically looks like we call it like PPV cube. The first 2-dimensional XYZ position, and the third dimension is the velocity. So here that's an example from GAFA H1 observation. Here that's XY plane, and the third dimension is the velocity. That's the observation we wanted to use to trace my 3D magnetic field. And for the spectroscopic observation, there are many kinds of such observation, like ionized gas, the neutral gas. And here we are thinking about using the neutral hydrogen emission observation to trace magnetic field. One reason is H1 gas is well mixed with dust, so it's easier to test it and compare it with dust polarization. So here, And another here is also a numerical example of H1 multi-phase ISM numerical simulation. And if we look at the hydrodynamic simulation, here that suggests the density distribution, we can see the density distribution has no any preferential direction, and it's more like isotropic distribution. But if we compare the hydrodynamic simulations with the MHD simulation of H1 emission gas, we can see the magnetic field actually can shape the structure of the H1 gas. And the mean magnetic direction here in this example is along the vertical direction. And you can see the apparent filamentary structure or striations along the mean magnetic field. Therefore, actually, the H1 gas can provide a new way to one can have the imprint of magnetic field. And another question you might in your mind is H1 neutral hydrogen H1 gas is neutral flow. Neutral flow means they cannot directly feel magnetic field. So why we are saying it's regulated by MHD simulation or MHD properties rather than hydrodynamic properties. So to answer this question, we have to say yes, in the astrophysics in ISM, we have neutral particles, neutral gas, neutral flows. But also we have ionized flow. Ionized flow can directly feel magnetic field, and of course, the behavior of ionized flow is MHD. And it's important to note that like the charged particle, ionized particles, they are not isolated from the neutral particles. New charged particles can collide with neutral particles. Therefore, if neutron and ions if they have frequent collisions, they can be well coupled. Therefore, in this case, if we have sufficient collisions between neutral gas and ionized gas, and the properties MHD properties from ions can be transferred to neutrons by the collision. And typically, the coupling scale between neutron and ions is larger than 0.01 parsec with just typical ISM conditions. And here, just if we other observation, the resolution is larger than these scales, we can see neutrons actually can also feel the magnetic field indirectly via the collision with ions. So it also has the MHD effect. And on the right side is another example of two fluid ISM simulation. In the top is ion density, ion velocity, and in the bottom is neutron density and the neutron velocity. And you can see actually the neutron density or neutron velocity, they are identical to the ion density and ion velocity. Therefore, neutrons can still feel MHD effect. Therefore, we can also use neutron gas to trace magnetic field. Just need to have the observation resolution larger than 0.01 parsec. Okay, so that's for the answer to our previous first question. How can we get the 3D distribution of magnetic field in ISM? We can use spectroscopic observation like neutral hydrogen, and we can use the galactic rotational curve. And the second question we needed to address is how can we get a 3D magnetic field in ISM using the spectroscopic observation? And here the 3D magnetic field, I mean the plane sky angle, the inclination angle of the magnetic field, and the total magnetic strength. And here where the one solution actually is anisotropy of MHD turbulence. And in yesterday Alex talk, we already know the ISM is pervasive with MHD turbulence, like here, that's a power spectrum measured by the Chepanov and Lazarian at 2010. So MHD turbulence is a very important component of ISM, and its anisotropy can provide us the new insight of a magnetic field. So I will briefly talk more about the anisotropy MHD turbulence. So firstly, MHD turbulence is like an interaction of anisotropic velocity eddies. And we can think about a simple picture. We have two eddies, they are moving in opposite direction. And the moving velocity of the eddy is the Alfvén velocity along parallel to the magnetic field. And in the perpendicular direction, the velocity is a turbulent velocity because the cascading is preferentially along the perpendicular direction. So if the two eddies they are colliding and they are destroyed, there is a critical balance. The time scale to destroy the eddy along the parallel direction is L parallel over R velocity equals to the time scale to destroy the I eddy along the perpendicular direction. It's the L perpendicular over the turbulent velocity. And if we assume turbulence is Kolmogorov turbulence, then we combine the two conditions, so we can get the anisotropy scaling of the eddies. That means here, this scaling, this equation means the perpendicular scale is much larger than the parallel scale is much larger than the perpendicular scale. As we can see in one of the example in the MHD turbulence simulation, here the segment is magnetic field and the background map is velocity. And we can see apparently the structures is elongating along the magnetic direction, and the parallel scale is larger than the perpendicular scale. So if we can know the direction of the parallel scale and we can know the elongation direction with the turbulent eddies, we can know actually the magnetic direction. So that's the anisotropy of edge turbulence. We are talking about the plane of sky elongation direction of the eddies, turbulent eddies, can tell us the plane of sky magnetic field angle. But the information contained in this map is not just the elongation direction. Another important parameter we can get from the observation is the aspect ratio, like the L parallel over the L perpendicular. And this ratio is regulated actually by inclination angle and magnetic strength. Why is this case? Because the elongation of the turbulent eddies along the magnetic field, it should be a 3D phenomenon instead of a 2D. Therefore, what we observed in 2D is a projected eddy. And the projection, therefore, can change the aspect ratio of the perpendicular parallel over the perpendicular. And this aspect ratio is also correlated with magnetic strength. We can think about if we have an extremely weak magnetic field like hydrodynamic turbulence. We don't expect any anisotropy. Therefore, the aspect ratio should be just 1. Therefore, the aspect ratio is well correlated with the inclination angle and magnetic strength. And such information can tell us how can we get the 3D magnetic field from just a 2D observations. And here another problem here is we have just one parameter aspect ratio, but we wanted to solve 2 variables, inclination angle and strength. That's not enough. So we need to find another parameters that good. And the curvature of magnetic field is also correlated with the inclination angle and strength. For instance, if we have very strong magnetic field, the magnetic field is just a straight line because it's very difficult to bend the magnetic field. Therefore, the curvature is very small. But if we have weak magnetic field is dynamically weak, then it's easy to bend the magnetic field to change the magnetic field morphology. Therefore, the curvature of magnetic field or the elongation curvature just will increase. And therefore, the curvature is well correlated with magnetic strength. But also we need to consider the observed curvature is also the projected one instead of a 3D parameter. Therefore, the curvature contains the information of inclination angle and the magnetic strength. So here, that's the information is enough. We have 2 parameters, aspect ratio, curvature, and the 2 parameters are enough to solve for the inclination angle and the strength and the strength. But to solve the correlation between the observed parameters and the 3D magnetic field, it's very challenging, and especially like the analytical, even if the analytical is also very difficult. Therefore, I'm thinking whether we have an easy way to do this job. Actually, machine learning is very is very good at solving the complex correlation between the observed features, the aspect ratio, curvature, and find the correlation with the 3D magnetic field, then to give the prediction. And here we are thinking about, okay, well, now we know here we have spectroscope observation, and we need 3 parameters, like 3 features of the observables: the plane of sky elongation, aspect ratio, and curvature. But what kind of such information we need? Like whether we need the information from the density field or velocity field. Because density field here, what from the observation also, like Manoj mentioned, density filament are not always perpendicular parallel to the magnetic field. That makes the prediction of the plane sky magnetic field orientation difficult. Like here is the example from the Planck observation, and here we can see the very cold and dense gas is perpendicular to the magnetic field. And also we have H1 simulations. We can see actually in some dense regions, the magnetic field is not necessarily parallel to the magnetic field, and it can be perpendicular to the magnetic field. But that's not the case for velocity. Therefore, velocity is a better trace of the magnetic field because it's always perpendicular, it's always parallel to the magnetic field, and it will not affected by like shock effect or compression of the from the turbulence. And next question we want to address is, okay, density field is easy. We have the column density observation, we have the intensity map, but where is the velocity information we can get in observation? So here we're thinking about the one important effect in the spectroscopic observation that's called velocity acoustics. And I will use several numerical experiments, simple numerical experiment to explain this effect. So here in the left panel, I set up a constant density scale in real space, XYZ space, and I assign this constant sphere with a turbulent velocity. And use this the real space setup, I transfer it to the velocity space. That makes which makes the spectroscopic position velocity space. And we can see actually the constant density sphere after transferred to the velocity space, its shape is highly distorted. It's no longer just a sphere. And if we take a slice from the one with the velocity, and we can observe some structures appear. And those structures do not exist in the real space because initially the setup is just constant density. Therefore, we can see actually velocity effect that maps the density from the real XYZ space into velocity space can create anisotropic intensive structures. And those structures are created by velocity effect, therefore it contains velocity information. And I will also show you another example that I simulate a synthetic spectroscope lines with a constant density cube but turbulent velocity cube. And here that's a synthetic channel map of the observation. And here the pink shaded area means the integration range to make the channel map. And let's see what will happen if we decrease the channel width or the integration range for the velocity space. And initially, if you remember, we don't have any structures in the integrated channel map because initially it's just the density field is constant. So there's no any real density structures in real space. But here, what you see here, if we integrate only the very narrow range of the velocity, we see a lot of filamentary structure appears, and those structures do not exist in real space. Therefore, they're purely created by the velocity effect. And you might also wonder, okay, we have the simple test with constant density field, we can clearly see the velocity effect. But what if we have the real density field, whether we have the mixture of density and velocity, or whether density velocity is still dominated over density in a realistic case? So here is another numerical example of the synthetic spectroscopic lines, but here I use the real density field of H1 gas. And here you can see when we decrease the channel width or the integration velocity ranges, the observed structure of the density gets changed. And finally, when we have the very narrow channel width, the structure what we observed is the same as the constant density case because it's purely dominated by the velocity effect. Therefore, we can say even if we are in real observation, we have density field, we have velocity field. When we have a narrow channel width, the fluctuation of the information contained in such a thin channel is dominated by the velocity information. And those thin velocity channel can be used to trace the magnetic field. So, okay, next part of my talk, I will talk more about the machine learning work we adopt. Here is an example of the convolutional neural network. That's a typical approach to extract the 2D feature for image features. So our input image for the neural network is a synthetic H1 thin channel map. So it's dominated by the velocity information. And then the input H1 channel map is convoluted with some kernels and kernels to do feature extraction. So the feature extraction includes the elongation, curvature, aspect ratio I mentioned. And finally, the neural network can find the correlation between those features and the magnetic field and give the prediction. And we use the different training data sets that's initiated with different turbulent velocity, sigma v, and different magnetic strengths to generalize to make the neural network extract a feature or find correlation in different physical conditions. And of course, in addition to just the convolutional neural network, in recent years, there are many different machine learning and different architectures. The different machine learning architectures, they have different advantages. And from our experiment, the vision transformer architecture is better at predicting the magnetic strength and the different. So it depends on the accuracy we wanted to achieve. We might to adopt different machine learning architectures, but here I just use a convolutional neural network as an example. And here is a comparison with ground truth, and in the top panel, that's a prediction outputted by the neural network. And here it includes 5 quantities: the plane of sky position angle, inclination angle gamma, magnetic strength, the alpha Mach number, which is the ratio between turbulent velocity and the alpha velocity, and also sonic Mach number. It's the turbulent velocity over the sound speed. And in the bottom panel, it's the ground truth of the 4 or 5 quantities. And we can see actually the machine learning approach can reconstruct the distribution of the 3D magnetic field and also some turbulent parameters very well. The only apparent inaccuracy is observed in the prediction of alpha Mach number MA, and here we can see the prediction is not so accurate as the ground truth. But here, as I mentioned before, different architectures has different advantages. If we adopt the vision transform architecture, it can predict the alpha Mach number better than the neural network. And for the machine learning prediction, actually, we also can care about what's the error in the prediction. So here we simply define the error sigma as a prediction, the absolute value of prediction over the ground truth. In the panel A, that's the error for the seen data. That means the prediction is made for the data that has been trained with the neural network. And we can see in this case, if the machine learning, if the machine has already seen the data, it can give very good prediction. The error for the angle prediction, plane sky angle, and the gamma prediction is less than 2 degrees. And the prediction of magnetic strength, the error is less than 0.05 microgauss, and it's also very accurate in predicting the alpha Mach number and MAs and MAs. But of course, if we want to apply the machine learning approach to observation, we cannot always know the physical condition in observation. So we should also test the machine learning's accuracy in predicting the magnetic field properties for unseen data. That means the data has not been trained with the neural network. And of course, we see if we input the machine with unseen data, the uncertainty significantly increase, and the uncertainty for the inclination angle and also the plane sky angle increase to like 10 degrees, and also the uncertainty for the magnetic field strength also increased to 1.1 microgauss. And also the uncertainty for the MA and MAs increases, but still, even if it increases, I think its prediction is also still very good because its uncertainty is not so large. So therefore, here at the next step, we apply the machine learning approach to H1 cloud. The two H1 cloud has different velocities, intermediate velocity cloud and a low velocity cloud. That means they are located in different positions in the Milky Way. And here to test the neural network predictions, we make a comparison with the velocity gradient, because velocity gradient has already been compared with Planck polarization or stellar polarization, confirm its ability to trace the 2D magnetic field orientation on the plane sky. Therefore, we use VGT as the velocity gradient technique as a benchmark, and we can see actually the machine learning prediction in the bottom panel has very good agreement with the velocity gradient measurement. But of course, the machine learning approach can do it more and can do the job better. We can also predict the inclination angle distribution and the magnetic strength, alpha Mach number, and the sonic Mach number. And here, I think here, because the two cloud has very different properties, like for the LVC cloud is very clumpy, and also IVC is very filamentary. And we can see actually the filamentary cloud is the filamentary IVC cloud. It has stronger magnetic field, and it's more like a super alphawinic and supersonic cloud. But for the clumpy LVC cloud, we didn't see apparent strong magnetic field in this region. Is relatively weak. Okay, so our last step right now, we have the 3D magnetic prediction from just the spectroscopic H1 observation. And we can use the velocity information from the H1 observation and apply it to the galactic rotational curve. Then we can solve the distance spatial position of the cloud in the Milky Way. Then we can get the 3D magnetic field distribution in 3D space in the galaxy. Okay, this is the application of machine learning approach to the diffuse ISN. But this approach is also can also be extended to star-forming regions. And the only difference is we need to adjust the input images for the neural network training. Like here, I use an example of the 13CO observations channel map. And we can use such a molecular emission line to study magnetic field in star-forming region. And of course, we can also use the synchrotron emission and still train it with neural network or another machine learning architectures, then we can get the magnetic information in ionized ISM or ICM. And also we can also use like polarized synchrotron emission, and many different types of observation can be applied to the machine learning approach and get different information on magnetic field in different phases of ISM. So here is
we're up 10 minutes. Yeah. You have 5 more
sorry?
minutes. You have
Okay,
5
thank
more
you.
minutes. Yeah.
So here is an example of the application of the neural network to the certain cell observations and in different physical conditions like sub-harmonic and super-harmonic. And in the left panel is say the neural network prediction, and we can see it has very good agreement with the actual magnetic field, but it's less accurate in predicting the alpha Mach number. In observation, we applied for star forming region, we applied the machine learning approach to the molecular cloud L1478. And here that's a comparison with the machine learning prediction and the Planck polarization. And we see actually the CM and the machine learning prediction has a very good agreement with Planck polarization in terms of the 2D magnetic field orientation. But of course, the advantage for the machine learning approach is able to get the 3D magnetic field inclination angle and also magnetic strength. So here we can construct a 3D magnetic field morphology like the inclination angle and MA in this cloud, and we find the mean inclination angle in this cloud is around 76 degrees, and it's almost a trans-harmonic cloud. Okay, so this is the last slide, and actually the machine learning, the potential, I think for the potential for machine learning approach is very huge. The key for machine learning approach is capable of extract features from just like a 2D image, and it can find a correlation with some physical quantities like magnetic field or turbulent properties like the compressibility, and give the prediction. So this would be very useful, like to predict another different physical parameters like the sonic Mach number MAs, because the MAs large MAs means it can induce significant shock effect, and which also induce small scale density fluctuation. Like here you can see difference for this one is the transonic intensity map, and here is the supersonic intensity map. And the difference is in the MAs induce different features in the observed 2D images, and the machine learning, actually machine can extract such a difference and predict the MAs. And also we can also predict the different fraction of MCT mode, like fast mode, alpha mode, and slow mode, because they have different properties. Like fast mode is perpendicular to the mean magnetic field, and alpha mode is parallel to the magnetic field. Therefore, different fraction of the different mode can also induce different features in the 2D observed images. And therefore, if we apply the machine learning techniques, and we can extract such difference and predict the fraction of MCT mode, and and of course the prospects of the machine learning is not just like the 2 examples I mentioned here, but also it can be used to study dust properties. And I think the potential of machine learning approach is very huge. Okay, that is all my talk. Thank you very much.
Thank you very much. Yeah. Okay, so we have question from audience. Go first, Bao.
Okay, hi, I'm Bao. Thank you so much for your nice talk. So I think I have 3 questions related to like technical, mostly technical one. So firstly, when you develop like the machine learning approach, so for any prediction for both the inclination angle, the inclination angle, the average Mach number, and also the sonic Mach number. So which means like you predict each output like just in one CNN, right? Only one prediction, right? Or you can do at the same time?
You can do it in the same time. It's a technique. Okay, it's a technique issue. When you set up your network, not just maybe not a network, or any machine learning architectures, you can like put different like not just one output. You can input just one input you have one input image, and in the output you can set up like 5 different parameters you want to predict, and the machine can find the correlation individually. Just maybe I can explain it in an easy way. You can do like a for loop. You can do a for loop, and like first training is for the inclination angle, and the second training is for the magnetic strength. The third training is for the alpha Mach number. And once the training is done, you make the prediction. It would be very, very fast, and you can output all the parameters together.
Yeah, I see that, because that if we're training for each one output for each CNN model, which means like we will get the accuracy for each parameter as well. But if we train like at the same time, so I guess it will have the degeneracy between the output in terms of accuracy. If we train that both these parameters at the same time, yeah.
Yes, I think that's correct, because there are some degeneracy, like both inclination angle or alpha Mach number can change the aspect ratio or change the curvature. So if you train them individually, it could be confused. Like the machine could be confused, and the accuracy is less than you train them simultaneously, because they can easily find. If you train them simultaneously, the machine can easily find. Okay, they can easily distinguish the degeneracy.
Okay, I see. And also, one question is about, because that you said that you also combine your work with also the galactic rotation curve that you shows in, I think, several slides. Yeah.
Yeah, sure.
The galactic rotation curve, when you combine that with the VGT one.
Yes.
For the H1, yeah.
Yeah, this one.
Yeah.
Our previous one?
Yeah, this one. So when we combine that it together, so we can get like 3D magnetic field in the 3D space as well. So I just wondering, like this one, you also assume like into one line of sight, or you can apply that to the whole diffuse medium, especially for the Milky Way.
If we want to use galactic rotational curve, is mostly just for the region around the galactic disk. And if it's above galactic disk, and the accuracy for galactic rotational curve is not so good, so it's not so accurate. So if you use this approach, it's mostly applicable to the galactic disk.
Okay, so this is applicable for tracing 3D magnetic field in galactic disk more than in the whole.
Yes, in the halo, if you want to trace the galactic magnetic field in the halo, it's better to use polarized synchrotron emission, because there is a Faraday rotation effect, and the Faraday rotation effect can maybe it's not easy to explain, but the Faraday rotation effect can induce deep correlation and can provide another distance information. So if you want to get a full picture of the 3D magnetic field in 3D space, you need to combine the H1 diffuse gas with galactic rotational curve, and also polarize the synchrotron emission with the Faraday rotation for the galactic halo.
Yeah, okay, thank you. That's a nice explanation. Yes, really thank you.
Any more questions? Oh, yeah.
Thank you for the nice talk. I have 2 questions. Can you go to the comparison with Planck?
You mean molecular cloud? Okay.
Right. So for the CNN prediction, you are using the channel maps to predict the magnetic field direction, and it is line of sight averaged. I think that should be like averaged, weighted by the density of gas. Planck is like weighted with the dust density. If the concentration between of dust has some variations, can you cause some sort of deviation naturally, so that the ground truth is actually different? Not.
Yes, I think you are correct. like for Planck, it's dust density weighted. But if we are using here, like for CNN, we're using just 13 CO, the weighting like density is different. For 13 CO, it's 30 CO is different from dust weighting. So that can make the difference. And that's why I think that's one reason we didn't see like perfect alignment with the Planck. But here, the point here is Planck is the I think the most reliable comparison for the CNN prediction. So we don't have other choice to make such a benchmark or comparison. And it's true if they have different density ratings, that can make the difference.
Do you expect a variation in dust concentration from simulations?
I'm not sure about the answer to this question, because I'm not sure where the dust concentration happens, in which density range, in which regions. So I cannot give an answer to this question. Sorry.
Also, you mentioned that at different channel map, you see different structures. But I thought the structures are identified in moment zero or in dust continuum. I don't see why you are identifying structures in channel maps.
Structures. Because here for our machine learning approach, how can we predict the magnetic field direction? Because we know if it's regulated by turbulence, turbulent velocity, the turbulent velocity structure is always elongating along the magnetic field lines. But for density, like moment zero, it can be either parallel or perpendicular. Like here, map here. Maybe this is just a dust. Let's say it's just a dust emission intensity map from Planck, and there can be structure that's perpendicular to the magnetic field. So if we use moment zero, it contains only density information, and the density can be either perpendicular or parallel to the magnetic field, and that can confuse the machine. In which case, I should use perpendicular. I should assume like the structure is perpendicular to the magnetic field. In which situation, I should assume the structure is parallel to the magnetic field. Therefore, we want to remove such a confusion to machine, so we use a channel map, because in channel map, the density effect is less significant and the structures are more elongating or parallel to the magnetic field, so the accuracy is better.
Okay, thank you.
Okay, so it's about time. So guys, thank our speaker again. Thank you very much. Then we can have tea time to 10:40. Yeah. Okay. Okay, thank you everyone. Giờ là mình nghĩ là mình đã biết cái issue của thật sự, tại vì mình để cái maybe output cho cái xin điều đó rồi thôi vậy đi về bài cái đó em đã hiểu cái cách mà giờ làm không nhưng mà dùng một bài rồi
cái lịch buổi chiều á có đổi á nên là anh biết chưa ạ? Dạ đúng không và anh thì hay là anh video thì lên trên
ok
dạ
mà em email cho anh chứ
ok hết rồi mà chỉ có anh học thêm anh là chưa nên là em mới
How you use one medium?
So I asked my cat.
Okay. Yeah.
Okay.
Okay. Come on, come on. Come on. Okay, so let's get started for second part of this session. So our first talk will be given by Jihe about studying magnetic field using both dust polarization and Riemann effect. Okay, so you can start whenever you are ready. So it's so I will give you a warning when you have 5 minutes left. Yeah. Okay, yeah.
Okay, hello everyone. I'm a research fellow in Kyushu University. I'm Jie Hwang, and I'll talk about the dust polarization and Riemann measurement test today. And this is my representative things. So for the introduction, in star formation scenarios, usually a few percent molecular clouds are collapsed by gravity. But already yesterday we said that the star formation efficiency in theoretically expected one is much larger than observed one. So we need to the mechanism to resist the gravitational collapse. So that is the turbulence and manifold. So two distinctive models in the strong manifold and weak manifold. So if manifold is strong, ionized particles are frozen along the manifold lines. So it is hard to move the neutral particles. So initially, the collapse along the manifold lines. So we can see the filamentary structures and diffusion regions manifold lines are perpendicular to the filamentary structure. But it's increasing the density inside the core clumps. So it is dragged the manifold and then change it. In case of supercritical clouds, so manifold cannot support the molecular clouds clumps against the gravity. It is collapsed very fast. So one model is to combine both models, and so initially it is magnetically subcritical, and then it's increasing, it changes the magnetic supercritical. So it is important to see the transition from the subcritical to supercritical. So to suggest that subcritical and supercritical, we need to determine magnetic strengths accurately. So we need to find the role of manifold in subforming process. So I only showed the two methods here, dust polarization and Riemann effect. Dust polarization, yesterday and today we said that already. So from the start, the additive magnetic dust grains are aligned with the magnetic field lines. So we can see the dust emission, it is the polarized. In case of Riemann effect, there is a magnetic on the molecular cloud of force. In the case due to the difference of magnetic angular magnetic momentum, so the line is split, and it is proportional to the magnetic strength. So it is the only method to directly estimate the line of sight magnetic strength. So in case of dust polarization, we used the indirect method to estimate the magnetic field strengths. That is the D-shape method. In strong fields, the strengths are aligned in the same directions, but due to the non-thermal gas motion, it is disturbed. So we can estimate that at-when velocity, and then we can estimate the magnetic field strengths. That is the D-shape method. However, there are a lot of uncertainties in the D-shape method. The first thing is the integration effect. If there is a turbulent eddies, several eddies along the line of sight, it is integrating or emission. And then we use the beam side to observe. So within the beam, it is the disturbed boundary line, so we can get only averaged value. So to solve these problems, angular dispersion functions or estimate the number of eddies along the line of sight to suggested, have suggested. And another issue is in the D-shape method, we assume the uniform field line. It is only disturbed by the non-thermal gas motion, but especially the uniform magnetic field is large scale magnetic field is non-uniform and can be covered. So if we this covered magnetic field as the mean field, the angle dispersion will estimated not properly. So we suggested that the model to hourglass or spiral like that to solve this one, or the Patel suggested the filter smoothing method, so assumed the mean magnetic orientation of the regions. So, but the limitation from previous observation and before my observation, it was we have estimated just one mean magnetic strength for the clouds or lumps. Instead of this, I have suggested to estimate the spatial distribution of magnetic strengths for the first time using the D-shape method. And from that magnetic strengths, I judged the relative strengths between magnetic field and gravity and turbulence. So those polarization works, I used the Bistro JCMT data and magma data. It is one of the rock survey done by AMA. So I used these 4 lines and 4 targets. I have estimated magnetic strengths for the 4 regions. So it looks like that. So there are a lot of details each targets, but I removed everything and I only showed the magnetic strength distribution and the meaning of that. So this is a OMC1 region, shows a converging hourglass-like pictures, and this is a monocellus R2, shows hoverplanetary system and spiral patterns. And this is a G28 magnetic lines looks like that, but it is changed in the AMA view, is perpendicular to the magnetic lines. And this is the G35, it is the AMA view. So we can show that the dense Hymes filamentous, but it is magnetic lines parallel to the filamentary structures. So to apply the new method of the DSET, we estimated the radial curvature of the polarization segments. So with the radial curvature can estimated from the 2 neighbor polarization segments, we can draw the circle. The polarization segments be tangent on the circle. Then we can assume that this circle's radius, that is the radial curvature. So if radial curvature is larger than the area, we apply the D-shape method. In that case, we can assume the uniform magnetic field within the box. However, if the radial curvature is smaller than the box size, in that case, the polarization angle dispersion overestimated and magnetic field strength is underestimated. So we calculated overall polarization map, estimated the radial curvature, and choose the box size, and by moving the box size, I calculated the angle dispersion. But in that case, we exclude the pixels having small radial curvature. That's the main point of this work. So it looks like in one pixel through the boxes and calculated mean angle, and changing, moving the boxes and calculated the mean filters and calculated the angle difference and estimated the dispersion within the box. And the main point is we don't use the pixels showing radial curvature smaller than the box size. So this is the result of the angle dispersion obtained by that method. This is OMC1, Monard, G28, G35. So we can see that the high density region usually showing high angular dispersion. So it is as increasing density, magnetic field lines trigger. So it looks like that. This is the volume density. So for the D-shape method, we need another factors, density and velocity dispersion. So I estimated the volume density from the dust emissions using the blackbody function. And then the velocity dispersion, we use the CATino or NTH plus, or in case of the ARMA data, we use the H13 plus data to show the velocity dispersion. So to use the three maps I showed before, we can get the finally magnetic field strengths toward the four regions. Then we can see that magnetic field strengths are strong in high density region compared to the diffuse region. So it is also the density also larger than it could be magnetic field strengths. The magnetic flux is increased in that region, so magnetic field strengths will be higher, and we can clearly show in the distribution map. And this is a mass to flux ratio. So we needed to calculate magnetic field strength to discuss the relative importance of magnetic field compared to the gravity. So this value is the critical value. We assume that the magnetized disk, it is in the disk, magnetic field and gravity are equivalent. And this is the observed value. So our observed value is larger than critical value. It means gravity is more dominant. And so we show this the red color. So we can see the dense regions, the gravity is more dominant. Magnetic field cannot support these clumpers, and they are collapsing or active star-forming regions. But after the large molecular clouds are supported by the magnetic field. So that's the overall result of my work. So I developed the new D-shape method and applied 4 distinctive star-forming regions, and the overall picture showed in diffuse region magnetic field strength is smaller, but compared to the gravity, magnetic field is much dominant, so it can support 4 overall structures. And then dense regions, magnetic field cannot support the regions, so it is gravitationally flexible. So we want to see